Well, welcome to Lecture 2 on induction. So let's just get right into it. There are three results that are very strongly related to induction. Okay, so first of all, just mathematical induction. If you have a family of statements indexed by the natural number n, and by that I mean that there's one statement for each n, and you have the properties that p of 1 is true, and that the nth statement being true implies the n plus 1th statement being true, then mathematical induction says that p of n is true for every positive natural number. So this is sometimes called weak induction, or I usually just think of it as standard induction. It is logically equivalent to what's known as strong induction. So strong induction is when you have a family of statements again, and again one for each n, and you suppose p of 1 is true, and you also have the property that if the statement true for all predecessors of n implies that p of n itself is true, then that means that p of n is true for all n greater than or equal to 1. So this one you can think of as you're assuming not just the case before n plus 1, like here you're assuming n and showing n plus 1 follows. Here you're assuming 1, 2, 3, 4, 5, all the way up to n minus 1, all are true, and showing then p of n follows. All right. So predecessor just means comes before n. That's just a condition k less than n. All right. So you can prove that this implies that, and you can prove that that implies this. I mean, we could do that. It's not that interesting. I've done it before in like a proofs class, but whatever. And then the other way to look at all this is the well-ordering principle. The well-ordering principle just says that every non-empty collection C, which is a subset of the positive integers, has the smallest number in it. All right, so sometimes this is effectively referred to as affectionately referred to as the WOP, well-ordering principle. And so this, fairly old mathematics, I think. So again, referencing Rotman's lovely book, Journey into Mathematics, An Introduction to Proof. It's a nice little book to have around. I'm borrowing heavily from it for this this lecture. This is a Dover book, which means it's not too bad. Anyway, Rotman mentions in here that induction was known at least back in the 1300s by Levi ben Gershon in 1321, and he also mentions Francesco M in 1557 was cited by Pascal, who we'll talk more about in the next lecture, by the way. And so anyway, of course, I have a strong suspicion that you could find induction in ancient mathematics of various different sorts and fashions if you went looking for it. It's such a natural idea that, if you can always take the next step, then you can always keep going, in some sense, right? But anyway, just a little bit of history there, which Rotman's always good for. Okay, so let's look at some examples. All right. So we'll start with first of all, definition. It's about time in this number theory course to define a prime. So here we go. What is a prime? A integer p greater than or equal to 2 is called a prime number if its only positive divisors are 1 and p. Okay, so for example, 2, 3, 5, 7, 11, 13, 19, 23, 29, 31, 37, 41, all primes. And so this page here is a collection of possibly cautionary tales. So what I'm doing with this next page here is illustrating some ways that possible induction proofs can go wrong. So here's example 1. Let p of n be the statement n squared minus n plus 41 is a prime number for n greater than or equal to 1. Let's call that f of n. All right. So it's easy enough to start checking. Like f of 1 is 41. Well, that's prime, right? F of 2 is 43. By the way, that's the next prime on this list I didn't list. f of 3 is 47. That's also prime. In fact, this continues all the way out to 40. Even all the way, 1, 2, 3, 4, all the way out to 40. The first 40 things that you enter into this polynomial give you prime numbers. Which is kind of neat, right? But when you get to 41, you cancel the minus 41 with the plus 41, and it gives you 41 squared. And that's not prime, right? Because it's got divisors of 41. So this is a statement which is true not just for the first, the second. In fact, this statement's true for the first 40 cases. But that's not enough, right? Like sometimes engineers do proofs like check the first case, check the second case, check the third case. Okay, it's true for all cases. But as you can see, that does not work, does it? And yet there are other situations where it seems like it works. So we just don't know yet, actually. Goldbach's conjecture is that every even number larger than or equal to 4 is the sum of two primes. So for example, 4 is 2 plus 2, 6 is 3 plus 3, 8 is 3 plus 5, 10 is 3 plus 7, which is also 5 plus 5, 12 is 5 plus 7, this goes on. So at the time Rotman wrote his book, I think this had been checked out to 10 to the 13th or something. There was no known counterexample, all right, and it's been kind of half proved, but it's not been proved. So that's why this is called a conjecture, because we don't have a proof that it's true, but we also have no known counterexample. So I think most people think Goldbach's conjecture is true, but if you could prove it, well, you wouldn't need to take this course. You could just name your university to have a like a named chair at. And I think it's worth some money too. Like this is a pretty big deal if you could prove that. Many have tried. Not me, but many. Example 3, here I want to illustrate another example where induction, so example 2 is not a place where induction fails, it's a place where induction, has induction failed here? I don't know if induction's really been tried here. It's unproved, so. If you can, the thing is, if you can find even one counterexample, game over, that f of 41 was enough to shoot this whole thing down. All right, let's go on here. So suppose P of n is a statement that n squared plus 3 is equal to n squared plus 1 for n greater than or equal to 1. I know if you have your algebra wits about you, you should be shouting to the heavens, no, you can't do that. Well, just hang with me here for a second. Suppose it's true. Suppose P of n is true. Consider P of n plus 1, all right? Well then, n plus 1 squared plus 3. Well, square that out, n squared plus 2n plus 1. All right, great. Now we can take this n squared and that 3 together. All right, I'll use some color coding here. So I'm taking this guy and this guy, putting them together. And see, I can convert this to that. So I'm converting these to n squared plus 1. And then the 2n plus 1 rides along. Oh, but look at that. That's n squared plus 2n plus 1, which is n plus 1 squared plus 1, which is the equality which is needed for P of n plus 1 to be true. See? N plus 1 squared plus 3 is equal to n plus 1 squared plus 1. Hooray! We've showed, we've showed 2 in this song and dance back here, right? We showed number 2 holds. P of n implies P of n plus 1 is true. It doesn't matter, though. Yeah, it doesn't matter because we didn't meet the other condition, which is that P of 1 is true. In fact, P of 1 is not true. P of 1 would be the statement that 4 is equal to 2, which of course is absurd. In fact, generally speaking, you can see that this fails because you can cancel n squared and you get 3 equals to 1. So this is the funny thing. It's like we can get... So example 1 shows you that the base case, even the first 40 cases holding, is not enough, because in this one, the induction step, the part 2 doesn't hold. And this one shows you that even though part 2 holds, part 1 not holding is game over, all right? Okay, so there's some cautionary tales, like that you can't half do the induction proofs. You got to have the whole thing. Base case matters, induction step matters. But let's look at an example which is a little bit more, well, famous. So this example often credited to Gauss as a school child. Supposedly he did this. Anyway, so here it is. The story goes, the kindergarten teacher was telling the kids to add up the numbers from 1 to 100, trying to buy themselves some time, and as soon as he asked the question, Gauss put down his slate and said, the answer, which is, I believe, 5,050. Let me see here. 100 times 101 divided by 2. Yeah, 50 is this answer. So the sum of the first 100 positive numbers is 5,050. Now, so child Gauss was supposedly having done this in like less than a minute. This was very annoying to the teacher. How did he do it? Well, he had some deep intuition for arithmetic is what it is. Now, he may not have actually done induction. He probably did something where he thought about pairing the numbers 1 with 99, 2 with 98, 3 with 97, and so forth. And so if you start with 1 to 100, you can kind of pair off the numbers and get 100, 100, 100, 100, 100, 100, 100, 100, until you get to the middle at 50 and you're left over. So you got 50 copies of 100 plus 50, which is 5,050. But it's more fun to think he used induction. So let's do that, since that's the point of this lecture at the moment. So the induction claim is that the sum from 1 to n is 1/2 n times n plus 1. All right, so first of all, p of 1 is true. Great. And if we assume p of n is true, that's usually called the induction hypothesis, right? Consider p of n plus 1. So we'll look at the sum 1 plus 2 plus 3 plus plus n plus 1. And what's that give us? Well, that by the induction hypothesis, we can replace the first. I'll use some color coding here again. We can replace these guys with this. That's the induction hypothesis, right? The n plus 1 rides along. And then we do something called algebra. I factored out a 1/2 n times n plus 1. That gave me an n here, all right? And then since I factored out 1/2, I put a 2 for that one, right? So I think of it this way. This n plus 1 term is becoming this 2 down here, all right? Anyway, algebra. And then just look at it. Well, that's 1/2 n plus 1 times n plus 1 plus 1. That's exactly the claim with n replaced with n plus 1. Therefore, p of n plus 1 is true. And we conclude by proof by mathematical induction that the sum of the numbers 1 through n is 1/2 n times n plus 1 for all positive integers. So there you go. That's a famous and standard example we should all see. Next example is, the other thing we can use induction for is just proving formulas that depend on n. So here's a pretty important one from calculus. This is the power rule, right? So if you remember the notation, x to the 0 is 1. So ddx of x, we can prove that's 1 from difference quotient stuff, whatever, in calculus. So suppose that's known for the sake of this discussion, okay? So dx is 1. And then, well, that's equal to 1 times x to the 0. So apparently p of 1 is true. Okay, great. Suppose inductively that it's true for n, all right? Consider the derivative of x to the n plus 1 power. Well, that's x times x to the n. That's the definition of the power function. Essentially, right? That's actually how you define x to the n plus 1 is this. We could talk more about that, I suppose, but stay focused here. And then the product rule says that it's the derivative of the first times the second plus the first times the derivative of the second, right? F prime g plus f g prime. And what do we have? We got x to the n plus, and then by the induction hypothesis, that's n x to the n minus 1, right? And then, again, algebra. That's n plus 1 times x to the n, which, tilt your head and squint, what do you got? You got n plus 1 times x to the n plus 1 minus 1. In other words, that's the power rule for n plus 1. So, lo and behold, we have shown that p of n plus 1 is true. Hence, the derivative of x to the n is n times x to the n minus 1 for all n in the natural numbers by mathematical induction. And so, that's kind of neat. Oftentimes when we face a formula which depends on n, it may well be that induction is a good tool to prove it, right? Okay, so these both have been examples of what I would call standard or weak induction. The last two examples are a little bit more number theoretic, and they're examples of, well, strong induction, actually. So let's look at these. Okay, every integer n greater than or equal to 2 is either a prime or a product of primes. Let's see how this is proved. So n equals 2 is true. And oh, by the way, the other thing I should mention is we can start inductions at other numbers than just 1, right? You can start inductions at like 10 or whatever. It just has to have a starting point. And that all ties back into the well-ordering principle. There has to be a least member, for a subset of positive integers. I mean, truth be told, you could also start inductions from negative numbers as long as it's got the success. As long as you have a subset of the integers with the successor property, you could do induction on such a set. Let's focus here. So suppose n equals 2 is true since 2 is prime. Let n be greater than 2, all right? If n is prime, then we're done, right? Because it's either a prime or product of primes. Okay, great. Otherwise, we'd like to show that the successors being a product of primes implies that n is a product of primes, all right? So if n is not prime, it's composite. And it being composite means it's a product of a and b, where a and b are both strictly less than n, okay? And you might notice then that a and b are predecessors of n, so using strong induction, we have that a and b are both products of primes. We say p, p prime, p prime prime, q, q prime, q prime prime, dot, 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 okay? Good notation. We don't really care too much about the details of the prime factorizations, right? And by the way, we'll talk more about prime factorizations in a few lectures. I'm just, these examples are helpful here for induction. We'll have a whole lecture. We just talk about primes, okay, guys? So we'll come back to that. This is just dipping our feet in the pond here, so to speak. Anyway, so AB is that times that, which means, hey, n is the product of primes. So we conclude by induction that p of n is true for all natural numbers. Strong induction, it's a shockingly powerful technique, really. And it's very easy for students to feel like it's cheating, and I understand their feeling, but they're wrong. Okay, so another example, every positive integer m has a factorization 2 to the k times m, all right? Where either k is greater than or equal to 0, where k is greater than or equal to 0 and m is a positive, is an odd integer, all right? The secret word for lecture 2 is tape measure. T-A-P-E-M-E-A-S-U-R-E. I guess it's secret words, but you get the idea. Tape measure. Hey, you can put a dash in it if it bothers you that it's 2 words. If we put a dash in it, it's just 1 word. I don't know. Anyway, I'll shut up. Okay, so base step. If n is equal to 1, well, that's 2 to the 0 times 1, so okay, good. Otherwise, inductively suppose that n is greater than or equal to 1, and that means that n is either odd or even, right? So if n is even, then n is equal to 2b, but b is a predecessor of n, which means we can assume that b has the form 2 to the k times m, where m is odd. But that means that n is equal to 2b times 2b, which is 2 to the k plus 1 times m. So lo and behold, it has the desired form. All right, so the claim is true for such n, right? And on the other hand, n could be odd, and if n is odd, well, then you're done, because n is equal to 2 to the 0 times m, where m is equal to n, so that's the right format, So in either case, whether n's even or odd, we see that it has a factorization n is equal to 2 to the k to the m using strong induction. So there you have it. Every positive integer has a factorization as 2 to some power times an odd integer. Surely we'll need that later in this course. Anyway, I hope that was a good review for you of induction. I really do hope you've seen induction before this. But if you're rusty on it, of course, ask me questions. I'm here to help. So that's it for lecture 2. I hope you like the length of this one more. Thanks.